back. Cool. Good morning, everyone. I'm Farbod, and I'm super excited to talk about a very interesting and exciting topic. In my opinion, that is different patterns of authentication for Internet of Things and in IoT applications. Amir, my colleague, and I will present this talk. We are part of a research team at Security Compass. We represent Security Compass. A few words about me. I've been in security research for more than a decade. My early background is in electrical engineering, control systems, artificial intelligence, and I've finished a long research on use of biometrics for crime reduction. A few words about Security Compass. Security Compass is a security company, obviously. We have different divisions, different business units, including training, advisory, and our landmark product is DiffieHellman that provides security guidelines for developers. It's an enterprise security management solution. And what we do is that we research different topics. And in the previous years, we have researched different aspects of IoT security, and we wrote different security requirements for IoT. And all that research led to this talk. Probably 5% of that research has been demonstrated and contributed to this talk. I will start from some general facts for a warm-up. Gartner predicts that there will be 13.5 billion IoT devices in 2020. And then I'm sure that you can read faster than I can explain. In 2012, average users used 17 passwords and 8.5 business passwords. And then a lot of business has been hindered by failed authentication. You can see that for more than 46% are frequently or very frequently have been hindered, blocked for authentication problem. And then there was a very recent article, a very recent research carried out by NIST that said that people are faced with security fatigue. It means that they don't pay attention to security as before. They have given up because of so many security requirements, so much security advice. And in my opinion, the single most important aspect of security is access control. And I think that the one big obstacle that we have for the rollout of IoT in the future is access control in IoT. Let me ask you, ask how many of you reuse their passwords? Not too many. How many of you reuse your passwords, but when you're asked that you reuse your password, you don't raise your hand? So I told you about our research that has led to this. We've been researching IoT in the past year, and it's been under a government-funded project by the government of Canada. And then we looked at different vulnerabilities in IoT, and one of the topics that we worked on was authentication. And we looked at different enablers and ideas of authentication, and then tried to build some patterns out of them. We realized that we are dealing with so many technologies, so many protocols, so many applications, and then we wanted to find the common patterns that we saw in them, the common denominator of all of them, because it wasn't really easy to write security guidelines for everything. You have to classify those patterns, those models into something, and then write security requirements for that thing. So we thought about the ways that we could classify those ideas, those patterns, into some specific models. So what we are going to do in this presentation is that we start with Internet of Things, we start with patterns, and then we look at different ideas and enablers of authentication, and then we propose this feature space, a number of features that we can extract from different patterns of authentication, and then we analyze the security requirements in those cases, and then we see how those patterns are used in practical scenarios in Internet of Things. So we have three phases: authentication and IoT, patterns, and then we'll look at the protocols. What is IoT? I'm sure that you're all familiar with IoT. In my opinion, again, these are the things that are new. These are new to the landscape that we're seeing. Physical access, people have infinite time to break down the system, tinker with the system. We have very low power devices that don't have much computation powers. We get emergent behavior. We have some behavior that we cannot predict in advance because every unit works separately and the result is something new. Something similar to emergent behavior that we see in the biological environment. And then we have privacy intrusion that because using the data intelligence, we can indirectly infer something about someone's identity. And we have denial of service attacks. And then one last thing is that we have numerous technologies and protocols there. And then we have to deal, all of these have the problem of interoperability. And then we have to, as security analysts, we have to look at many different technologies. And that was the problem that we have to look at and deal with in this research and this I'm going to talk about in this presentation. So what type of authentication needs do we have in IoT? The people have to authenticate into devices, devices have to authenticate into services, and the services need to authenticate to each other. So what do we mean by patterns? So what are patterns? Patterns are reusable solutions to common problems in a specific context. There are many books on patterns, like I'm sure that you're familiar with the early work of Gang of Four on design patterns. We're trying to build some authentication patterns. And then self-announcement means that, is claiming identity. Again, why patterns? Because patterns give us common understanding of a problem. When we talk to each other, when we name a pattern, we don't have to go from the beginning and talk about all the details. When we say pattern A, we reach a common understanding. And then when we want to write security requirements, we can write security requirements for the patterns, not for the particular technologies. And then we can extract matching conditions, and then we can reuse information, obviously. And for the pattern, we have to specify examples, context, problems, solution, structure. This is a very long presentation. I have to be very quick. Sorry for that. So we tried to identify some features. We tried to propose some features for different authentication systems. And this is the best that we could do. I'm not claiming that we have found the solution for everything. We haven't found the theory of everything. But looking at different patterns, I think that these are the features that are most useful for discriminating between patterns. I will go through them, and throughout the presentation, we'll see them over and over again. And what we are going to do in this presentation is that we will see how these different features make difference in those for those technologies and those patterns, and we'll see how those patterns are used in different IoT technologies. So what are these features? You can use isolated authentication, centralized authentication, and federated authentication. We'll explain these later. The key to authentication is a shared key that is shared between two entities. And this shared key could be either symmetric or asymmetric. Symmetric shared knowledge means that you have the same thing that the other side has. So you both have the same things. But in asymmetric shared knowledge, you may have something that the other side has something that corresponds to that, like private and public key. Public and private key is the common example of that. And then you can directly verify that shared knowledge, or you can indirectly verify the shared knowledge. For example, you can send something to someone to encrypt that with their key and then send it back to you. That's called indirect verification. And another very important aspect of authentication is building a channel. I'm going to emphasize throughout the presentation that building a channel, a secure channel, a trustable channel, is as important as authentication. Actually, authentication doesn't have any value if the channel that is built after it is not reliable. So, but we have looked at different patterns and different way of communication, interactions between entities, and we have realized that we can cluster them, we can classify them into two major categories. One is that when you build a channel before you do the authentication, regardless of the authentication, you build a channel and then do the authentication on the channel. The other approach is that you do the authentication, and as a result of authentication, you gain a shared key between you that will be the basis of that channel. So we'll see examples of all of these. So this is our feature space coming from a signal processing background. I like to extract features from everything. I want to put everything on access, except countries. So on X, I have direct and indirect verification. We have asymmetric, and we have secure channel before or after authentication. I use those letters as abbreviations. So if I call channel DSB, for example, it shows that it uses direct verification. It uses symmetric shared knowledge, and it establishes the channel before the authentication. And then we have those different domains, those different spheres. If I could show this in 4 dimensions, I would do that. But because we are familiar with 3 dimensions, then I put that dimension on in a different. I demonstrated that in a different way. And these are 4 main questions that we realize that we have to ask ourselves about any pattern. Does the pattern exhaust shared knowledge? Does it transfer shared knowledge too much? Does it create a basis for a channel that protects against sniffing and protects against replay attack and relay attack? And does it provide forward secrecy? I'll talk about forward secrecy later. So I think Amir will present the rest of the presentation. Not the rest of the presentation, I think. We'll switch back and forth.
Yeah. So first of all, a quick introduction of myself. I'm soon celebrating my 2nd year at Security Compass as an application security researcher. Before that, I was and research assistant at Information Security Center of Excellence at University of New Brunswick. So at this point, I want to describe those 3 authentication topologies we showed in the previous slide. The first one and the most simple one is isolated authentication, which means the point is the authenticator is bind with the resource. So the user simply sends the request and the proof of identity to the resource, which acts as the authenticator. So it's simple request and response. So once it's verified, the user gets access to the resource. The next pattern is centralized authentication, in which a centralized authenticator server acts as the authenticator for all of the entities around. So the user sends the proof of identity, gets proof of authentication, and then using that, like say token, it asks for the resource from the resource server. In some cases, in some examples, for example, in SAM, the resource also verifies the token with the authentication server as well. So next, we move on to the federated authentication. In federated authentication, it's so different authentication domains recognize each other's proof of identity. For example, if service A in domain red is authenticated using the shared knowledge A, that authenticated a user with shared knowledge A, that user is also authenticated in domain B, which have another services and authenticators as well. So the example is single sign-on we are using every day with Facebook, Google, and other authenticators. So now we move on to the actual authentication patterns, and we put them into different buckets. The first one is password authentication protocol, which is the very simple one. In this pattern, the client sends the username and password directly without no secure channel clear text to the server, and the server responds. Very simple. So we call this pattern, we put this pattern in DS0 category, which means the authentication is direct. That means the client sends the credentials over the channel to the server, the actual credentials. And then it's symmetric because server and client both know the same shared knowledge. And there is no, we put 0 because there is no secure channel. So everything is on clear text. So this two-way handshake is mostly used in point-to-point protocols. So the problem is obviously that the password is clear text and can be easily sniffed. And also the password can be reused by another entities for the same authentication to get the same service. To solve the clear text problem, encrypted PAP is introduced. So the mechanism is pretty much the same. The only difference is that the username and password are encrypted and sent over the server. So it's still direct authentication, sends the credentials over the channel, still encrypted, but it's encrypted, but still it sends the actual credentials. Shared knowledge is symmetric, but we put B, which means the secure channel is established before the authentication, which means we have encryption and send the credential through the secure channel. And the little s means that the encryption, the secure channel is based on shared key. So the problem with the encrypted PAP is that if there is a man in the middle, it can capture the credentials even if it's encrypted, and later, without awareness of the client, can replay the credentials to the server and get access. So this two-way handshake is still used is useful for P2P protocols. It solves the clear text password problem, but it still has the problem of man in the middle, and the trust channel is an issue. So next pattern is Challenge Handshake Authentication Protocol, CHAP, which is an indirect one. So the main difference is that instead of sending the credentials directly, it sends indirectly the proof that I am the authentic user. So in this pattern, the server challenges the client with a nonce, and then the client, using the symmetric shared knowledge, calculates the response and send it back to the server. So with this, the server can verify that the answer is correct and authorizes the client. So this three-way handshake is used in Wi-Fi web networks, and the Nonce Defend protects against that man-in-the-middle and reply attack, because Nonce is different every time. If the man-in-the-middle capture the challenge or nonce, next time that would be a different one, so it cannot authenticate itself to the server. But the problem is still that in this scenario, server authenticates the client, but the client does not know the server is the authentic server, so there's no mutual authentication. And also the clients have to repeat this process, this negotiation, every time for every single request. So that brings us to four-way handshake, which is an ISD. So the four-way handshake is pretty much the same as the CHAP, but there are two main differences. One is that both server and client authenticate each other using the PMK, pairwise master key. So it's still symmetric shared knowledge between these two. So the server challenges the client, and the client also challenges the server to make sure that they both are on the same page. The second difference is that the PTK, which is the session key, so the client creates a session key. After authentication, the communication is happening using that session key to encrypt the communication. So basically, authentication is happening, and the secure channel is established after authentication. So that's the T is after authentication. So this pattern is used in Wi-Fi WPA2, which solves the problem of mutual authentication, but still PMK is shared with everyone. For example, in a Wi-Fi network, everyone knows the PMK, the master key, the wireless password, say. And if you walk into a coffee shop and someone is already sitting there and connected to the network, it's got the PMK. So once you request for authentication, that node can calculate your session key as well and sniff your communications. At this point, I hand over the presentation back to Farbod to talk to you about the importance of secure channel.
All right, thanks. So let me, let's ask yourself, what are we doing here? Let's not lose the sight of everything. We demonstrated we are going through different patterns, and we're looking at the evolution of patterns here to find those common elements there. So every pattern that we look at, we could actually specify all of these in like formal methods, but that wouldn't be as helpful. The reason that we took these patterns out of context was that we wanted to show these ideas behind this. You may ask yourself, why would we need a simple pattern like this? Because in some of the IoT application, it's inevitable to use them. There are some devices that cannot do anything more than like point-to-point authentication. So when we look at all these patterns, if you look at the pattern notation on the top, you see that we have been able to identify those features that I explained in the beginning, and then assign one acronym to each of them. So we looked at these different patterns, and we identified the problems that we could associate with them and the security problems that we had. So next time that you see that one of these patterns is used in any of the in any of the IoT scenarios, or for any of the IoT applications, any of the technologies, you realize that something could go wrong. And then by knowing that what could go wrong, then you can probably take care of that with some additional security measures. So we looked at all these patterns, and we could assign an acronym to all of them, ISD. But one another thing that we found out was that the establishing a secure channel is as important as the authentication itself. Actually, there's no value in authentication. I told that in the beginning of the presentation. There's no value in authentication if we cannot establish a channel after that. Let's look at, for example, one of the patterns that we went through. What was wrong with this CHAP scenario? So you send the nonce, the client encrypts the nonce encrypts the channel, sends back to server, and server accepts or rejects the request. But what can we go from there? Nowhere, because it's still with the next request, you still have to repeat the same thing. You have to send the channel, you have to sign it, send it back, and then send the request. So the value of authentication, in my opinion, is the channel that it helps us to build. So again, in general, there's no escape from building a secure channel. Trust is still sustained. After you do the authentication, everything is dependent on the channel. So what happens after you do the authentication? You get an access token, and with the next request, you have to just send that access token. So that your security, you will be as secure as your access token. And so now we look at the different ways of establishing a secure channel, and then we look at the brilliant ideas of building a communication channel and secure channel. One of the greatest ideas that has been put forward in the history of, I think, security has been DiffieHellman algorithm. And the family of algorithms that are similar to DiffieHellman. And the idea behind DiffieHellman algorithm is that I want to build two entities, want to build a secure channel between each other without having any shared knowledge. And the brilliance of DiffieHellman is that you can talk to someone on a secure channel without having anything in common. And if someone comes between you, even if someone has been there for the entire time, that person cannot decrypt your communication. And how does it work? It works like this in the simplest form. Suppose I want to talk to Amir. I generate a pair of keys, private key and password, private key and public key. I send the public key to Amir, and then I ask Amir to generate a random number that he only knows, and then encrypt that and send to me. Because I have the private key that I have generated, I can decrypt that, and then from that moment, we can use that random number to communicate. So if someone is here, an entity, a man in the middle, if someone is here for the entire communication, they cannot decrypt the communication, and they cannot intercept the communication. So that is the idea behind DiffieHellman. We call this pattern 00B because it doesn't have any shared knowledge. It doesn't obviously do any symmetric or asymmetric verification of that knowledge, and it only builds a channel. And it builds the channel before authentication, but it could be a very valuable basis for the authentication, for the next step of authentication. So we have different variations of DiffieHellman algorithm. In ephemeral DiffieHellman algorithm, we generate different private keys each time. There's a huge overhead because of that. But it has forward secrecy because if one of the next set of keys are stolen, then they cannot go back and decrypt all of the session and access all of the data all of the previous data. But it had a very huge overhead and an elliptic curve. These are all details. I think that this presentation will be uploaded somewhere, and then you can look at all of these. In ECDHE, there have been some algorithm to make the calculation of keys faster, and it has also forward secrecy. But DH doesn't provide any authentication. We were able to build a secure channel, but we didn't have any authentication. What could we do after that? We can build a secure channel, and then we can do authentication using any method over that. One of the common methods is RSA ECDHE. It means that we establish the channel, and then we use RSA keys or any asymmetric algorithm to sign a message, and then through that we can authenticate the other part. So why do we call this pattern IAB? I want to ask you to, when you look at the pattern, just think about those three axes. This is indirect verification because this is I because of indirect verification. We don't send over the shared knowledge. The shared knowledge is asymmetric, IAB, I'm talking about IAB. And the B means that the channel is established before the authentication is started. So the channel could be established regardless of failed or successful authentication. And the final pattern that we want to present is the new family of patterns that is called Paik, and is used in Thread protocol and Zigbee protocol in very new IoT protocols. And there's been a very nice innovation in those type of patterns, and they have enabled us to use symmetric authentication with the same ideas as before. So it has very low computational requirements. It's a new family of algorithm that enables us to authenticate the other part and build a secure channel, but without use of any asymmetric algorithm. No public key management, or it has forward secrecy. The most important thing is that it also has forward secrecy. Paik is used in thread protocol, a variation of Paik that is called JPaik. Paik by juggling is used in thread protocol. Also, Zigbee can use SKKE, which has the same characteristics of Paik. So how much time do we have? So finally, we'll look at different protocols and technologies, and we'll see how these patterns are used in practice in those IoT technologies. We'll look at XMPP. We'll look at different message keying protocols, Zigbee thread, RFID, and HyperCAD and UDDI. Just very quickly, should I describe this one? Okay. So XMPP protocol, I'm sure that you're familiar with this, is a XML-based protocol that IoT devices use to send messages. It's based on SASL, and SASL has a stack of different types of authentication. But when we went through all of those patterns of, that are used in SASL, we realized that we can map them to one of the patterns that we had shown in the previous slide. So in SASL, for example, I would just explain a few of them. In SASL, you can have plain, clear text use of password, which is isolated DS0, or if you go down the list, you'll have OAuth, which is centralized indirect verification, either by symmetric or asymmetric, and the channel is established before. And then you have federated ISP. We have to go through the details of each of these. We won't have time, but I'm sure that this presentation will be somewhere soon, and you will actually do the exercise yourself, and you can look at the patterns and identify these different features in them. So I think Amir will explain the publish and subscribe architecture.
So at this point, I would like to talk about publish-subscribe architecture as an example of that three topologies we talked about in authentication: centralized, isolated, and federated. So generally, publish-subscribe protocols, if you are not aware of, are messaging communication patterns in which a single broker is responsible for message delivery. So specifically in IoT environments, publish-subscribe is very useful and practical since we've got low-powered, very thin nodes which cannot do lots of computations. For example, a temperature sensor senses the temperature, sends it to a server, and it sleeps. And so the nature of IoT devices is that they are very weak, and the connection between these nodes are usually intermittent. So a resourceful broker in between can handle everything for them. So simply publishers publish a message to a specific topic to the broker, and subscribers, which are other devices or services or servers, can subscribe to those topics and fetch those messages. Most of the publish-subscribe protocols use SASL for authentication purposes. So here I want to show an example of those three authentication topologies we talked about: isolated, centralized, and federated. So in isolated identity management and authentication, as we said, the server and the authenticator or the resource are both the same. So here the broker authenticates every node around it. So there is a single service and a single authentication. So it's very simple to realize, but the drawback is it's not very scalable, and obviously it's single point of failure. If the broker fails, any authentication in the system fails. So to solve that problem of scalability, another topology, which is centralized identity management, has been evolved, which means there is a separate authenticator. Every entity in the system authenticate to that single authenticator. So multiple services in one domain can authenticate to the server and communicate with other entities. But still, there is the problem of the single point of failure. We still have single authenticator. It's separate from the resource, but still single authenticator. To overcome this issue, there are multiple authenticator added in different domains. So multiple services can use their authenticator to authenticate everyone else. So different domains can be integrated, and so that makes the system more efficient and scalable. Single sign-on, as I mentioned, is one of the examples which we are using every day. This flexibility is with the cost of more complexity to the system. So at this point, so knowing all of these, now Farbod is going to describe few specific protocols which are used in IoT and compare the authentication pattern. The first protocol is ZigBee. Farbod?
Yeah, again, we look at different patterns, and we ended with the Paik pattern that we could use symmetric authentication in, and we could get all of the benefits of asymmetric authentication that we had in the SSL communication. So Paik is used in ZigBee, and Paik is used in Thread too. And there are also great ideas that have been used in ZigBee protocol, and both ZigBee and Thread. And start with ZigBee. Do you know that ZigBee is a low-power wireless mesh network? It's an alternative to Wi-Fi for low-capability devices. And it has two stages of discovery and joining. And each device comes with a preloaded key. And as we explained, it uses SKKE, which is very close, like in its features and characteristics, it's very similar to Paik algorithm. And it has IST, in our patterns, has IST pattern, which means that it does indirect verification of the shared knowledge. It's based on symmetric keys, and the channel is established after the authentication. And it uses a federated model of authentication because of different routers. As a result of authentication, there are different keys that are generated. Network key is common between all nodes. Link keys are pairwise nodes, and master keys are the shared knowledge that is loaded into the devices. Another example is Thread protocol. Again, Thread protocol is used in the Nest devices can either use wireless or they can use Thread protocols if they are low capability and low power. And it's also another an alternative to Wi-Fi protocol. There is another new concept that is introduced in Thread protocol, and that is the concept of commissioner that does the authentication. The commissioning has two stages. First, the commissioner has to be authenticated, and then all the devices authenticate to that commissioner. So if we want to describe this in terms of the patterns that we proposed, there are two stages. The commissioner has to authenticate to network. The commissioner doesn't have to have all the network keys, but it uses centralized ISP, and then after it's authenticated using a commissioning passphrase, that is a symmetric shared knowledge. Everything else authenticates to that node, and then again, both the stages are centralized ISP. Thread uses JPEG, as I said, uses juggling in the Paik, but it still has the same pattern, indirect verification, symmetric keys, and the channel is established before the authentication. What's the difference between channel before the authentication and after the authentication? If the channel is established before the authentication, if the authentication fails, you still have the channel. But if the channel is established as a result of authentication, you cannot have failed authentication and have the secure channel. So the last class of examples that we see is RFID and NFC. The reason that we put RFID and NFC here was that these are the examples of very low power devices that cannot do anything. And we see that there are cases, there are scenarios that we don't have any other options except using the simplest form of authentication. There are three possible ways of authenticating in RFID systems. The RFID needs to authenticate the reader needs to authenticate the RFID. And in the simplest form, the server with each request only sends the password, and this is the DS0 password. If we use the cover coding, a method of encryption between the RFID and this reader, we have DSB. And then another method is based on indirect verification. There will be one key that is on RFID, and we have the same key on the reader, and then they send a random number, and we call that IS0 or ISB based on the encrypted channel. And the cover coding is very simple. It's only XOR. If you're familiar with RFID, it only uses a simple form of secure channel, and that is only XORing that with a random number. So in RFID, we have the same patterns. We have a simple pattern of, as I said, password, isolated password that is sent by each request to the reader, to the tag. It's easy to eavesdrop. It's easy to sniff because it uses RF communication. And then it's easy to brute force. There's no solution to that. You can have tens of RFID tags here, and then you can have a reader that sends the kill command to all of them with different passwords, and you can brute force them. But sometimes it's the only possible solution. You have to accept the risk. And then, as I said, you have the same patterns that we showed, like with sending a nonce. This pattern it can be used in RFID. We're trying to show that these are the patterns. These are the only possible patterns, and then they are repeated in actual applications, in actual protocols and technologies. And finally, for example, it would be ideal if we could use asymmetric algorithm on the RFID, but most of the RFID tags could not carry out any asymmetric algorithm. So this is an example of where you know what the best pattern is, but you cannot implement that on the device. So I want to conclude our entire discussion here. Again, I want to ask you to try to identify these different features when you look at different patterns of authentication in IoT or in any other context. We talk about direct and indirect verification of SK. We talk about asymmetric or symmetric SK, and we talk about the channel, establishing the channel before and after the authentication. And then we told that there are three different types of identity management: isolated, centralized, and federated. And all of these different patterns, different characteristics, bring their own advantages and disadvantages. We show that there are numerous technologies, different technologies. Patterns help us to gain a common understanding of those, of the characteristics of the technologies. And we try to propose and build a feature space that facilitates classification using these specific features. The advantage of having a feature space is that by looking at these letters, these acronyms, they immediately highlight the security requirements and the computational power that we need. This summary of what we learned was that if we, when you see that some pattern uses direct verification of SK, you know that you have to put more emphasis on the secure channel. It may exhaust SK by reusing it. And if you have asymmetric SK, then sometimes you need more computation power. Again, for secure channel, if it's affected by the choice of SK, and then you have to look at sniffing, replay attack, relay attack, and forward secrecy. These are the things that you have to ask yourself each time you come across a new pattern. And then we have ICF, centralized, isolated, and federated, and then you have to ask a question about how you want to manage the keys, and then do you want to have a single point of failure or not. So the presentation summary, we highlighted the importance of identifying patterns for authentication. We propose a feature space. We analyze various patterns and show the security problems with them. And we demonstrate how these patterns are used in various technologies. And now, if you have any question, we'll be more than glad to take them. Yes.
So if you have devices that have a lot of computation power, like RAM, CPU, whatever else they need, and battery, is there an ideal solution for like a high-powered environment where you don't have the constraint on the endpoint?
Good question. I think the high-powered devices are like the servers that we have on web application. We can put all of the different security measures there. You should use SSL, and then you should use asymmetric algorithm and a symmetric algorithm. You can have different layers of authentication. You don't need to use any of the new innovations like the ones that we had in JPEG, we had in Thread. It will be like the traditional client-server model that we have. Any other questions? No. That's it. Okay. Thanks for your time, and thanks for coming, and hope that you have gained something from this presentation. Thank you.
Thank you.